All right, welcome to the 20th lecture, I think, or 21st maybe. Oh, let's forget how many we have. Yeah, today is March 3rd, actually 18th lecture. Okay. So today, I think last time we stopped somewhere around the comparison results to between gamma spaces and various other models for infinity spaces and group-like infinity spaces. So just a brief recollection of what we did last time. So we started with a model structure. We constructed a model structure on gamma objects in simplicial sets. And the way we constructed it was by taking the left Bala's field localization of one of the traditional model structures with object-wise weak equivalences, for example, projective, injective, or generalized 3D structure. So if you don't know what that means, the last one is defined in the paper by Berger and Morgake. I can tell you which one it is, but you just search for generalized 3D structure. We perform a left Gauss field localization and two maps such that when you map them to some fixed object X, you recover precisely the Siegel maps. And the second map from the initial pre-sheaf to the representable pre-sheaf of 0, that just ensures that the zeroth space will be contractible. So this condition here. And together, these two conditions precisely give you what Siegel, or perhaps not Siegel, but somebody like Anderson, I think, called special gamma objects. These just model homotopy coherent commutative monoids. And today, let me first start by mentioning very briefly, just at least to resolve some of the confusion, how what we did with gamma spaces connects to some other models you may have heard of. And one of those models is algebras. Algebras over operads. And of course, the probably one of the most famous operads is E-infinity operad, which by definition is an operad such that the map to the terminal operad, which is precisely the commutative operad, is a weak equivalence. And the action of the symmetric group on the nth symmetric group on the nth component of that operad is a free action. Then algebras over E-infinity operad, over this type of E-infinity operad, were one of the models. I think that was first proposed by Peter May, as a model for infinite loop spaces, or more precisely in our case, homotopy coherent commutative infinity monoids. And you can, it's not so difficult to prove that, yeah, there is a clone equivalence between gamma spaces equipped with the model structure we just constructed here. and algebras over infinity operands. So on algebras over the infinity operand, you equip them with the transferred model structure. So here we use the transferred. So it's transferred along the right adjoint, which forgets the operatic action and simply extracts the underlying object. The forgetful functor to simply show sets. And you can already see maybe one of the advantages of gamma spaces is much easier to write down an example of a gamma space in a practical situation than it is to write down an action of the of one specific model of the E-infinity operand. And in some cases, it can be easy, but then the E-infinity operand will have to be like more complicated. For example, if you are willing to replace the infinity operand with the so-called operand of Lego disks, then in principle you can write down, encode more examples more easily, and the operand of Lego disks is also has this property. And just as another remark, gamma spaces are also equivalent to algebras over the commutative operand in the quasi-categorical sense. So that's why I put the capital letter Q, so Q refers to quasi-categorical. Quasi-categorical algebra. So for example, as presented in Lurie's higher algebra, or there are also other related models, for example, the models using dendroidal sets are all equivalent to this one. So just so this is basically so that you are aware of what the other approaches are. And let me also say just a couple of words about group-like gamma spaces. So these actually are gamma spaces where all elements are invertible with respect to the product, with respect to the product encoded by the gamma space. And how can we express this in a sort of in the language of pre-sheaves and left Balansfield localizations? Well, one way to express the fact that multiplication is invertible is to require that the so-called shear map, which sends a pair xy to the pair x comma x times y, so this map has to be an invertible map, because then if you want to compute the inverse to some element x, you simply take the if this map is a weak equivalence, you simply take the pre-image or the inverse map and apply it to x comma identity, and then this will construct for you a pair x comma y such that y is the inverse of x. And this shear map can itself be obtained by mapping into X a second map constructed out of representable pre-sheaves. And more precisely, as you can see at the right side, x1 times x1 is simply the space of maps from the coproduct of two representable pre-sheaves of 1. And the left side, of course, is just given by the representable pre-sheaf of true. And the map from left to right, well, it's a map out of the coproduct. So I have to specify two components separately for you, and the component for the left summing will simply be the inclusion of 1 into 2, which corresponds in the language here on the right side, which corresponds to the projection map that takes a multipliable pair and extracts its first component. And the second sorry, I said inclusion map. I should have been more accurate. So it may be an inclusion of pre-sheaves, but on the level of finite sets, this corresponds to a map from 2 to 1 that sends all elements to the base point except for the element 1, which is sent to itself. So that's not quite an inclusion. So here iota 0 is given by a map of finite sets that sends everything to the base point except that 1 is mapped to 1. And the map mu is for the second summing on the right. And this map is induced by the map that we previously discussed. It's a map that induces multiplication, and it sends both elements 1 and 2 to 1. So these two maps taken together implement the shear map here. So if we add this map to the list of maps that must be inverted by a left pulse field localization here, so if we add it to this list here, then the resulting model structure will now encode group-like gamma spaces. So these will be special gamma spaces for which the shear map is a weak equivalence. So these are known as very special gamma spaces. Or perhaps simply as group-like gamma spaces, which perhaps is a more convenient terminology. And the resulting model structure also admits a Quillen equivalence. So tilde means an equivalence between the very special model structure on gamma spaces. Oh, sorry, I should have. No, sorry, that's not what I meant here. I guess what I meant here is that the resulting adjunction between special gamma spaces and very special gamma spaces is you can think of it as an adjunction that implements the homotropic group completion. Oops. So the left adjoint forces a special gamma space to become very special, and that's precisely what a homotropic group completion should be. And do notice that in our case, since these two model categories on left and right are both left Bowles field localizations of the same model category, the underlying functors for this adjunction are just identity functors. So in case you are confused as to how the identity functor can implement homotropic group completion, let me point out that the fibrant objects here and here are quite different. here the fiber objects are special gamma spaces, and here on the right, the fiber objects are very special gamma spaces. So when you send an object from left to right, on the right side, it will be weakly equivalent to some very special gamma space, which will be precisely its homotopy group completion. So do not allow the presence of non-fiber objects to confuse you. So what will ultimately happen is that the fiber replacement functor will perform the homotopy group completion for you. And this model category on the right is one of many models for connective spectra and also known as infinite loop spaces. And connective spectra are can also be defined in a variety of other ways, like, for example, the conditional definition using a sequence of spaces which are connected using bonding maps. And but ultimately, the resulting model category is equivalent to very special gamma spaces. And that was the reason behind the success of Siegel's machine. So this, by which I mean simply this construction here, maybe not expressed using the language of model categories, but that was added a few years later by Bausfield and Friedlander. So the success of Siegel's machine is explained by the fact that it's very easy to work with this model category, and it's very easy to construct examples inside here. And I think I may have mentioned one example previously. Yes, if you have a small category with a symmetric monoidal structure, then you can construct gamma objects in a sort of relatively straightforward manner by sending the object n to a certain relatively simple category. And this allows you to define the homotopy group completion of the resulting nerve very easily. And this is precisely what algebraic or topological K-theory is. So the homotopy group completion functor is precisely this. Okay, any questions about this page here before we move on to other topics? All right, let me now point out that these machines, so previously we studied two things. We studied how simplicial objects can be used to model categories, or more precisely, homotopy coherent categories. And we also studied how gamma objects can be used to model homotopy coherent commutative monoids. Let me point out that it's very easy to combine such machines together. And here I wrote down one example of how to do this. If we can consider, say, special gamma objects, meaning contravariant functors from gamma to complete Siegel spaces. so special gamma objects in complete Siegel spaces. In the language of categories, this will be simply a contravariant functor to the category of functors from delta up to simplicial sets. And this can be also reformulated by in a variety of ways. First of all, there is nothing special about the order of gamma and delta. We can also consider a complete Siegel object valued in special gamma spaces. And finally, and this perhaps is a bit more closer to actual practice, we can put gamma and delta on equal footing and consider a contravariant functor from gamma times delta to simplicial sets. And then this functor must satisfy a special gamma condition in the first factor and complete Siegel conditions in the second factor. So from the general theory explained above, we know that such objects must model homotopy coherent commutative monoids in infinity 1 categories, and which of course are also known as symmetric monoidal infinity 1 categories. And here I immediately wrote down an example to illustrate this idea. So the Bordism category that we previously discussed, and let me pull out the previous discussion so that you have something to compare. Let's see. Yes. So as before, we fix a dimension D at least 0. So this will be the dimension of our Bordisms. And we are now defining a functor as indicated. And of course, as before, this functor will factor through the nerve functor. So really what we are going to do, they will define a pre-sheaf valued in small categories, and then we will apply the nerve functor. So how is, so given some objects in gamma and delta, which we denote by L in angle brackets and M in square brackets, we are now going to construct a second category, a category that gives you the value of your pre-sheaf on this pair. So if we have so this category is going to be extremely similar to what we defined last time. There will be one more ingredient. So let's recall very briefly what we did last time. The category we defined last time had as objects, it had what we called Bordisms. A Bordism consisted, first of all, of a d-dimensional smooth manifold capital M, which you think of it as basically it's the Bordism itself plus a small open neighborhood, which is called the color or the germ, depending on your preference. So that's the part along which you are going to glue stuff in the future. And this manifold is partitioned in a certain way using something called a cut tuple. A cut tuple is just, according to this definition, a cut tuple on a smooth manifold capital M is a sequence of cuts. And the cut was previously defined. Well, you can see the formal definition here. It's a partition of your manifold into 3 parts using some height function h from m to real numbers, so that the 3 subsets will be the preimages of the negative ray, 0, and the positive ray. And geometrically, this looks like, let me give you a good geometric picture. Can I not draw a proper picture here? I mean, oh yes, here. Geometrically, this looks like your height function projects your bordism onto the horizontal line, and this part will be, say, m less than 0. This codimension 1 slice will be m equals 0, and everything else to the right will be m greater than 0. And in a cut tuple, we have a sequence of such cuts. Here is one, here is another, here is one more. It's not connected here, and it's fine. And here is the last one. These cuts must follow each other in the order, in the most obvious possible order. When you say one cut precedes another, if it's less than 0 part is a subset of the other less than 0 part. So that was a data we previously had, and it allows you to compose bordisms. And now we add just one more bit of data. It's a map called capital P. Capital P is a map from M to the finite set L. So this is a map. Well, I mean, it's a smooth map, but of course this is just a finite set interpreted as a discrete manifold of finitely many points. Finite set or finite pointed set. And so here's an example of a bordism on the left. Has many connected components. And here's the finite set. It's in our case L equals 3. So the finite set has elements 1 to 3, and it also has a base point. So the base point in our paper is called the trash bin. And there's a reason for that, is because it's called a trash bin, because that's you discard. Once you discard stuff into it, it can no longer be used for anything useful. So the map capital P, so that's the map capital P, by the way. What it does, it maps your entire bordism into this discrete set here. Which therefore partitions your bordism into some components, into some summons, where each summon can have 1 or 0 or more, I guess, connected components. And I guess here I didn't really indicate, but it's perfectly fine to have also an empty preimage. It's not prohibited. So that's a data you assign. And if you recall now our interpretation of Siegel gamma objects, what you assign to an object of gamma, like L, you should think of whatever you assign as a multipliable L tuple of objects in your in whatever structure you are trying to define. So here you see a multipliable triple of bordisms. And how do you multiply them? Well, multiplication or monoidal structure in our case is or should be given by disjoint union. What is a disjoint union? Well, it will simply, you would think of like, take this summand and this summand, and now we should perceive them as a single summand. So how is this implemented using the language of gamma spaces? Well, in fact, it's very easy. So here in the green, I have an example of such a map. So it's a map from 3 to, I guess, to 1, let's say. Yeah, why not 1? So this map sends 1 and 2 to 1, and it sends 3 to the base point, and also the base point, of course, also goes to the base point. And what is the meaning of such a map? Well, the meaning of such a map is that you have a multipliable triple, and this map, what it does, it puts the third part in the trash bin, so it is, in a sense, effectively discarded. And the first two are multiplied, meaning we take their disjoint union. And if you see what happens in the composite map, so here, for example, this will be mapped to the trash bin, and this also stays in the trash bin. And now this entire thing here maps to a single element 1 here. And this means this entire collection of, say, 4 connected components is now perceived as a single element in a tuple. Or in other words, we effectively choose a disjoint union of this Bordism and this Bordism. So that's, it may seem almost tautological to you, and of course that's because it is. So not much is happening here. It's a fairly tautological construction, but it does resolve the problem that we encountered, which is, technically speaking, how exactly do we define disjoint union of manifolds so that it is strictly associative? Well, there is no obvious way to do it in the usual framework. But here we define an honest functor from an honest contravariant functor from gamma to the category of small categories. Okay, any questions about this example and in general how Bordisms interact with the gamma structure? All right, let me move on to higher categories now, finally. So, I mean, you probably all have heard at least something about higher categories, like a true category has objects. Between objects, you have one morphisms, and between one morphisms with the same source and target, you have two morphisms. And perhaps you can try then to generalize this to arbitrary number of levels of morphisms. You can have k morphisms, Between k morphisms with the same sourcing target, you can have k plus 1 morphisms. But it is maybe important at this point to point out that in principle, once you go to a categorical level 2 and higher, you have at least two different possible generalizations of what a higher category should be. And one of those is what is called a bicategory. In a bicategory, you have objects, you have one morphisms. That's similar to how an ordinary category works. And if you have true one morphisms with the same sourcing target, you have a true morphism between. You can have a true morphism between them. There is another structure which is also very natural. It's called a double category, and it's depicted on the right. In a double category, you have objects, you have horizontal one morphisms, or simply horizontal morphisms. You have vertical one morphisms. And finally, if you have a diagram consisting of two horizontal morphisms and two vertical morphisms, whose sources and targets match as indicated, you can have what is called a true morphism or a true cell sometimes between them. And there are natural examples on both sides. In fact, there is one example that fits both here and here. So let me give you a very typical example of a bicategory. Its objects are, say, algebras or commutative rings, if you want, commutative rings. Its one morphisms will be bimodules. A bimodule is an abelian group equipped with two actions of two different commutative rings on the left and right. So it's both a left module and a right module. And composition of one morphisms is given by a tensor product of bimodules. So if I have a bimodule M from A to B, and a bimodule N from B to C, where A, B, and C are commutative rings, I can compose them by tensoring them over B. And that's how composition works for bimodules. And finally, I have true morphisms, which sometimes are called intertwiners. And these are just maps that are linear on both sides, linear with respect to the action of A and B. So if I have true bimodules, M and M prime, then a morphism, a true morphism, from M to M prime will be a map, a linear map, that is linear with respect to the action of A and the action of B. And yeah, true morphisms are composed in the obvious fashion, so that also works fine. Now, the very same example can also be made to fit the framework of double categories just as easily, if not more easily, than the previous example. So let me pick maybe a better color. Objects of this double category will be commutative rings as before. Horizontal one-morphisms will be bimodules precisely as indicated on the left. I guess this purple color is not very different from black. Yeah, I'm going to be a bit more different. Maybe this. But now, let's recall we also have another very natural notion of a one morphism of commutative rings, and these are just homomorphisms in the usual sense. We study them in your algebra class, right? Homomorphisms of rings, commutative rings, are perfectly legitimate notions of morphisms. So now, what are the true cells? Well, the true cells now should be let me maybe put in some letters. So let's say we have a true cell. A, B, C, and D are commutative rings. We have bimodule M from A to B and a bimodule N from C to D. And two homomorphisms from A to C called F and from B to D called G. Well, what exactly is a true cell connecting filling out this data? Well, perhaps it may help to write this as a composition. And now I'm kind of like running out of space. Let's see, how do I squeeze? I think this tool should help me. Let's see. Okay, now please squeeze. Okay. And I took A and B with it. Now, these two guys can be sort of composed by writing down M transited with D, where D is taken to be a left module over B. So how is D a left module over B? Well, the action of B on capital D is given by applying first the homomorphism G to a given element in capital B, and then the resulting element on D in D acts here by left multiplication. So that's a perfectly legitimate construction. This is called extension of scalars. And on the right side, so let's notice D is also a right module over itself, and M is a left A module. And on the right side, we will be composing these two guys. And how are these composed? Well, this will be just N as a right D module and as a left A module. And again, you see that technically N, capital N, is a left C module. So how is a left C module turned into a left A module? Well, the action of A is given by applying the homomorphism F to an element of A, and then C does act on capital N from the left. So that's a true cell will now be an AD bilinear map between the indicated modules. And you can see now, in principle, using the universal property of tensor products, we could have rewritten this even a bit more easily than what I wrote. I could have also written down, say, an AB bilinear map from M to capital N as an AB bimodule, where we should turn into an AB bimodule by applying the homomorphisms on both sides. So here we use the F and G to construct the corresponding actions. Okay, and this is really not, I should have separated this like this. Like this. Yeah, so in principle, both structures have a right to exist. Both of them are interesting. For us, however, it's the bicategories that are important. And the reason for that is ultimately because we will be interested in ideas such as duality, so dual objects and dual morphisms, and dualizability of morphisms. And this is most easily expressed in the language of bicategories and similar structures. And the reason for that is that in a double category, in principle, you can have many different, quite different notions of generalizability because you can have generalizability with respect to horizontal morphisms and generalizability with respect to vertical morphisms. And these two generalizabilities can be very, very different. And in the case of a Bordism category, however, we only really have one natural notion of a generalizability, and that's what we want for the cobordism hypothesis. And that's why we will be trying mostly to formalize the left side now as opposed to the right side. But the right side is in fact very easy to formalize. It is precisely what will happen when you start iterating the construction of complete Siegel objects. So previously we talked about well, here I talked for simplicial sets, but you can replace simplicial sets with any other model category. I'm not sure if I ever talked about a more general context. Well, yeah, I did say, I think, I didn't write it, but I did say that simplicial sets can be replaced by any other model category, Cartesian model category, let's say. And imagine you replace simplicial sets here with, again, with complete Siegel spaces. So it will be functors from delta op to functors from delta op to simplicial sets. So you iterate this construction twice. And what happens is you get a model for what would be rightfully called double infinity one categories. So you will naturally see pictures like this one. And yeah, that's how double infinity categories work. So to get bicategories or infinity bicategories for us, or also known as infinity true categories, we will need to impose some additional conditions. The point of additional conditions is to sort of to get a picture like this one. From a picture like this one, we must ensure that there is no such thing as a non-invertible vertical morphism. So if we force all vertical morphisms to be invertible, having invertible morphisms is fine, and this will allow us to force every picture to look like this. And the condition that forces vertical morphisms to be invertible in a n-fold Siegel object is called the globularity condition. The meaning of the globularity condition is that a priori, if you have a simplicial object that encodes some categorical structure, so here V is some other category that we are enriching in. And for the purposes of examples we are considering right now, you can take V to be complete Siegel spaces itself. So what you really should be thinking about on the right side, for example, you can take V should be functors from delta up to simplicial sets equipped with a complete Siegel space model structure. And then here you will see a simplicial object in simplicial objects in simplicial sets. This encodes an a double infinity category. And the globularity condition says if you extract the zeros part of the simplicial object, which is supposed to encode the object of objects, well, a priori, the object of objects can be any object of capital V. Like is to say, it can be encoding any infinity 1 category. So these guys encode infinity 1 categories. So, so this object corresponds to points in this diagram and vertical morphisms. But as I just previously mentioned, in order to collapse true cells to pictures like this one, we must force the vertical maps to be invertible. So instead of an arbitrary infinity 1 category, I really want the zeros object to be an infinity groupoid. And one way to express this is to say that, yeah, x0 is weakly equivalent to an infinity groupoid. But how do we express an infinity groupoid in an arbitrary model category V? Well, one way to express it is to say is given by taking the terminal object in V and transferring it with some simplicial set. So a simplicial set encodes some infinity groupoid. Or if you don't like this transferring, which is a special case of a weighted colimit, you can also say take the homotopy colimit of some small diagram for which its values are the terminal object on each object. So it's a constant diagram valued in the terminal object, and you check its homotopy colimit. And that's what you call an infinity groupoid inside this category V in which we are enriching. So the globularity condition requires us that x0 is not an arbitrary object, but is weakly equivalent to an object of this form, which is how we defined infinity groupoids inside some arbitrary infinity category capital V in which we are enriching. And in particular, for the case of V being complete Siegel spaces, this definition will reproduce precisely what is called a homotopy constant simplicial objects, which means basically you don't depend on this argument. For all simplicities, you get weakly equivalent spaces. And this is precisely how infinity groupoids are encoded inside all complete Siegel spaces. Okay, any questions about the globularity condition and what it means? Let me now, as briefly as before, mention how to encode globularity as a left Biospheric localization. First, let me make a bit more precise what I mentioned already in this line. Here is how we encode infinity groupoids inside capital V. So strictly speaking, this is formalized using a Quillen adjunction. Here on the right side, you have simplicial sets, which you really think as being equipped with a Kahn-Quillen model structure. So this is basically just infinity groupoids. Then we require a Quillen adjunction, where the Reich adjoint, you think of it as an inclusion. It's the inclusion of infinity groupoids into all objects of V. And the left adjoint, you think of it at least morally as some kind of construction that inverts all morphisms and possibly also all higher morphisms up to homotopy. So that's basically what it is. And to formalize the fact that this Reich adjoint is really an inclusion, we also require that the derived co-unit map is a weak equivalence, which means if you start with a simplicial set here, you apply the derived right adjoint functor, and then you apply the derived left adjoint functor to go back. You will end up here, and whatever you end up here with must be weakly equivalent to whatever you started with here initially. So sending an infinity groupoid to capital V and then going back doesn't change an infinity groupoid. So this truly means that infinity groupoids sit inside capital V as a full infinity subcategory. So that's how we formalize precisely the idea that capital V, whatever category we are enriching in, contains infinity groupoids inside of it. Sorry. And do notice this also implies that at least under a very, very mild assumption that V is a combinatorial model category, this implies also that there is a set of morphisms, capital S and capital V, such that the induced adjunction from the left Boles-Field localization of capital V at S, the induced adjunction, Quillen adjunction, will be a Quillen equivalence. So if you are in the setting of these two assumptions, it is always possible to localize capital V to make it equivalent to infinity groupoids. If you recall now what left Boles-Field localizations do, you may recall that basically left Boles-Field localization extracts a full subcategory here that is closed under infinity limits, and for which the inclusion functor has a left adjoint. But that's precisely what these assumptions here state anyway. So in other words, basically they say up to a Quillen equivalence, simply shows sets R a left Boles-Field localization of V. So this property should not be too surprising for you. It's basically a tautology, and the only reason we had to impose this combinatoriality condition is to guarantee that capital S is a set as opposed to a proper class. So now with these observations in mind, it is quite easy to formalize the globularity condition. So oh yeah, and let me mention maybe one more thing is that if V and capital S are as above here, so if the category of capital V satisfies these assumptions, then the category of simplicial objects in V also satisfies the same assumptions, and probably I should have spelled this explicitly. So simplicial objects in V and S prime satisfy the assumption star on the left. Here. Why is this useful? It's useful, of course, because we want to iterate the construction of a complete Siegel space. And this remark makes an observation that this iteration process will preserve this property star.
So sorry, V is a model category. Yeah.
Yes.
Okay.
Yeah, maybe I should have said this somewhere. So this is a model category. And we think of capital V as maybe encoding some type of categorical structure. For example, capital V could be infinity groupoids, infinity 1 categories, could be encoding infinity n categories, could be encoding symmetric monoidal infinity 1 categories, could be encoding any other categorical structure. As long as it contains infinity groupoids, we are good to go. Okay. More questions? Please ask more questions. We have relatively few questions today. I think that's because Yegor is not here today somehow. Okay, so now the globular model structure can be encoded by as a left Boles localization of simplicial objects in V. So you take simplicial objects in V and you encode them you equip them with the usual projective, injective, or ready model structure, depending on your preference. As long as object-wise weak equivalences are object-wise weak equivalences, you are good to go. And you take a left-Balanced weak localization with respect to a set of morphism S prime, which is given by chanceling the representable pre-sheaf of a zero simplex with an arbitrary element of capital S, where capital S was constructed here. And the meaning of this left Balanced localization, if you write down the locality condition with respect to S prime here, forces for a local object X. So a local object will be, maybe I should be breaking this down. X is local with respect to S prime. If and only if its zeroth object is S local. And according to what we said here, being S local means precisely you are in that essential image of simplicial sets inside capital V. In other words, that's what we mean when we say X0 is an infinity groupoid. And of course, let's not forget the globularity condition is not the only one you need. You also need the completeness condition and the Siegel condition, of course. So the actual model structure we need here will be the complete globular Siegel model structure on simplicial objects in the model category capital V. And we add these other two morphisms as before. So the five objects in the complete globular Siegel model structure, I should probably say this more explicitly, five objects or local objects, maybe I should be more precise, local objects, I guess. Local objects will be satisfying three properties. They will be satisfying the Siegel condition. The completeness condition. And the globularity condition. X0 is an infinity groupoid. And the reason we previously did not mention any globularity condition when we talked about ordinary complete Siegel spaces valued in simplicial sets is, of course, when X0 is a simplicial set, that's automatically an infinity groupoid. So for infinity 1 categories, the globularity condition is tautological. It's always true. But in general, it must be imposed separately. Okay, any questions so far?
So why do we have S prime equals y 0 tensor S?
Oh, that's precisely to ensure this equivalence here. So we want S prime local object. So what does it mean to be S prime local? it means you pick an arbitrary element in S prime, and let's say, and now I'm running out of space, so let me write it here. So you pick an arbitrary element, let's say G from A to B is an arbitrary element of capital S. Then the corresponding morphism given by transiting with 0, and I'm really running out of space, so A this is, I guess, one of those situations where inserting a new page is beneficial. Okay, now we have space. So what does it mean? So let's say S prime is given by transiting the representable object of 0 with S. Or more precisely, we really take this. What does it mean to be S prime local? So X is S prime local. By definition means the derived map in space, which, if you recall, about 2 months ago, we gave several definitions, so pick your favorite. From Y0 tensor G to X is a weak equivalence. And now let's expand. So this functor is left adjoint to the evaluation at 0. So I can equivalently say mapping G into X0 is a weak equivalence. So here you have a weak equivalence of simplicial sets, and here you also have a weak equivalence of simplicial sets. But G is an arbitrary element of S, so by definition, this means X0 is S local. So this transiting with the representable object of 0 is just a way to impose this S locality condition simply on the zeros object and nothing else. Oh, by the way, is the meaning of this transiting clear to everybody? Or should we write down a definition?
I would like the definition, please.
Yes, of course. So in general, what is this transor, the way I wrote it here, is a functor from, I guess, pre-sheaves of sets on delta. So let me write it in full generality. So you have a functor from pre-sheaves of sets on C times V, true. So this is called transor. Pre-sheaves on the same C with values in V. And how does this work exactly? Well, giving two objects, say F, a pre-sheaf of sets, and say capital A, an object of V, I map them to the pre-sheaf here that sends an object C in capital C to F of C tensor A. And what is F of C tensor A? Well, F of C is a set, right? And A is an object of capital V. So how do we tensor elements of, how do we tensor sets and objects of V? Well, this is simply the operation that takes, so if you have some G as sec and some capital A and object of V, you usually assign it to a coproduct of G copies of capital A. So you usually get a coproduct of that many copies of capital A.
Thank you. Thank you.
All right. More questions? All right, and now we are finally ready to iterate. So the model category of globular complete n-fold single objects in V is simply defined by iterating the construction we just discussed, the construction of part B here. So part B is really the one that matters, actually. Part A is just an auxiliary technical construction. So maybe we should like box. That's the important stuff. So if n equals 0, we just take capital V. And if n is greater than 0, then we simply take the iteration of this construction in part B. So we take the model category of globular complete single objects valued in the model category of globular complete n-1 fold single objects in V, capital V. And that's how higher, well, this is what is called an N category. Informally, perhaps you could call it an N category object in V. And of course, N here really means infinity N. In other words, or perhaps some people will call it a weak N category object to distinguish it from a strict N category object, which need not be as general. And here I listed some examples of useful values for capital V. And of course, for us, a very important case is V is simplicial sets. That gives you infinity N categories. Another example is just V is just ordinary sets. Ordinary sets gives you just what is called an N category in the usual sense, in the or sometimes called a weak N category. So that's the original, so to say, the original sort of object of study of higher category theory. Before infinity N categories, there were N categories, like tri-categories and quadruple categories, perhaps, yeah. Other interesting examples include, for example, chain complexes. That gives you something called differential breakage N categories. And we will be interested in something a bit more complicated than simplicial sets, but not radically more difficult. And the examples we will be interested in, well, in the first approximation, you could say we will be interested in simplicial presheaves on the Cartesian side, equipped with a Czech model structure. This would give us something we would call smooth infinity n categories. These objects, these structures allow us to encode the notion of a smooth family of objects or a smooth family of morphisms. And this is absolutely crucial to formulating a correct definition of a functorial field theory, because we want a functorial field theory to send a smooth family to a smooth family. And if you look in the paper, the actual thing actually used in the paper will be even a bit more difficult than that. And it may look a bit weird on the first sight, on the first look, but it will be simplicial pre-sheaves on the product of two copies of the Cartesian site. And the first copy has the same meaning as before. It encodes smooth families, and that's the one that we will equip with the Czech model structure. And its meaning is unchanged, but let me also note that this copy generalizes to more general variants of Cartesian spaces, such as super Cartesian spaces, which will be responsible for supersymmetry and other types of sites. The second copy is somewhat has a somewhat special purpose. It will encode isotropies. And we will talk more about isotropies a bit later, but they have some crucial properties that, for example, allow you for Bordisms to have duals, which otherwise simply would not be possible. And this part of this factor of Cartesian spaces will be equipped with a model structure that has way more weak equivalence. This is called the shape model structure. And the shape model structure and simplicial pre-sheaves on Cartesian spaces is equivalent to just ordinary simplicial sets with a Kahn-Quillen model structure. And so you may ask, well, why bother with this additional factor? Let's just throw it out and just work with simplicial pre-sheaves on cart as here. If these two guys are Quillen equivalent, why bother with something that there's a Quillen equivalence here? Between these two model categories, there is a Quillen equivalence. So why bother to use something much more complicated? Well, the answer here is that first, it actually turns out to be, so in fact, this version is what we used in the first 3 revisions of the paper. But the last revision uses this more complicated thing, because first, it's a bit easier to write down the definition in this setting. And secondly, it simplifies the proof considerably, because suddenly when you have the second direction, you can take stocks in this direction, which turns out to be a very important technical tool somewhere in the middle of our proof, which simplifies considerably and allows us to cut out maybe 2 pages of material from this, or maybe several more pages actually. This we will explain when we'll explain this aspect when we come to it, so to say. All right, so as you can see, there's a huge potential. And of course, I didn't even mention all possible examples. Of course, you can, for example, take, I don't know, V equals gamma spaces, right? Of course, this gives you what is called a symmetric monoidal infinity n categories. And of course, you can throw gamma everywhere. You will get like symmetric monoidal smooth infinity n categories. So for example, you can add it here. You get smooth symmetric monoidal infinity n categories. So that's perhaps what I should have mentioned as a very last thing for today. So let me pick a nice special color just to make make clear for you guys that this is something very special. So V, okay, that's not very special. Let me pick something different. Okay, maybe this one. V, somehow these are not so saturated. Maybe this one. V equals simply show P-sheaves cart times gamma times cart. Yeah, that's what actual our setup is. So maybe I should be a bit more precise. Oh, sorry, it crashed. Not sure why now periodically it crashes. One moment, let me reconnect. Okay, can you guys see the screen again?
Yes, yes.
Thanks. And of course, it destroyed my work. Fantastic. I think it's telling me it's time to end now. So, so V. This is very good. All those colors look much better in the. So V equals simply show pre-sheaves on cart times gamma times cart. That's what our setup is. So that's what we'll call smooth symmetric monoidal. Infinity n category. And that's precisely what is used in the paper. There's no more additions here. That's it. This is the final answer to life, universe, and everything. And this will be what we will actually use in the paper. And I think that's a perfectly good moment to stop because it's 10:30. So yeah. So let's see if you guys have any questions left for today.
I have a question about the example on the functor board N.
So somewhere above.
It seems that I didn't understand this example.
Okay, so that's probably here, right?
Yes.
So board D is a generalization of the construction without gamma. So if we strip away gamma, previously we talked about a complete Siegel object valued in simplicial sets, which was constructed as the object-wise nerve of the complete Siegel object valued in categories. And this complete Siegel object assigns to a simplex M the nerve of the following category. Its objects are what we call boardisms. Let me put, I hope it doesn't crash. Of course, it somehow resets. I don't know why does like splitting the screen. No, okay. And here, previously where is it? Yes, right here. So previously we just did all of this without gamma. So we constructed a single object of d-dimensional Bordisms as a simplicial object valuing simplicial sets. In fact, it is actually a simplicial object valued in small categories. It sends a simplex M to the small category whose objects are what we call Bordisms. These are by definition pairs consisting of a d-dimensional smooth manifold capital M, which is what is depicted by this entire picture here. The entire thing is M. And the only other data is capital C is what we call a cut tuple. A cut tuple is given by a sequence of cuts. This one, this one, this one, and this one. And each cut.
Objects are manifolds and morphisms.
Morphisms are, let me show you the morphisms. Morphisms are what is called a cut-respecting embedding of Bordism, meaning you have two such objects as depicted in this picture, and then one of them is embedded into the other using an open embedding. So basically you embed it as an open subset of another such Bordism. And not just arbitrary open subset, it has to satisfy these two conditions. Well, the first one tells you the cuts must be the same, basically. The cuts must be the same. The new cuts must be the same as the old cuts. So cuts must be compatible. And the second condition says the image of this open subset must contain the core of the new Bordism. So what is a core? The core is just this area in between the leftmost cut and the rightmost cut. So we throw away the colors here and here, and what remains is a compact topological space, which is what we call the core. And so the image of this open embedding must contain the core. It can also contain other stuff, but it, at the very least, must contain the core. So basically, geometrically, this simply, these two conditions geometrically look like you have one Bordism, and then you may expand the colors on each side just a little bit, and that's your codomain. So the only thing a morphism does, it expands colors a little bit. So you can say morphisms are basically what they do is just all what it does, it expands colors. Nothing else. There is not really nothing else happening at this point. And in the case of gamma object, the only additional ingredient will be a partition of your Bordism into some disjoint parts, like here and here and here. And morphisms must also respect this partition, so they must send a part. They must respect this partitioning into parts. That's the only new ingredient.
Okay, thank you.
All
right, more questions?
If V is chain complexes, so then we have differential graded n categories, and what are these differentials then?
What are what, sorry? What was the question, sir?
This differential, because when we
The differential
what are the
gradient
differentials?
refers to the fact that in a chain complex you have gradings, and between those gradings you have a differential. So differential gradient is just another way of saying enriched in chain complexes. This simply means enriched in chain complexes. For example, a differential gradient algebra is an algebra enriched in chain complexes. A differential gradient module is a module enriched in chain complexes. So a differential gradient N category is an N category where N morphisms no longer form a set, but rather they form a more rich structure, which is a chain complex. So instead of a set of N morphisms, you have a chain complex of N morphisms. And that's why we call it a differential gradient N category.
Okay, and can we give some explicit example of this?
Well, for N equals 1, it's fairly easy, right? So N equals 1, these are fairly well known. So, ordinary category enriched in chain complexes will be an example. And these are fairly common in homological algebra. In homological algebra, they basically deal with categories enriched in chain complexes all the time. If you want something that is not necessarily strict, right? So here I mentioned strict categories, but our setup is more general. As an example of a non-strict category, maybe you can take something like various constructions, perhaps something like a Fukaya category could be an example, perhaps. Or anything constructed geometrically, like various categories constructed from Morse theory and Floer theory. Anything that involves constructing a category where somehow objects and morphisms have a geometric nature. Composition is given something like an intersection or fiber product, or pick your favorite. And morphisms themselves, you can add and subtract them by formally like in a free abelian group. And the chain complex, well, the degree will be corresponding to something like dimension of your geometric object. Then the differentials will be taken, well, again, this depends on the concrete problem you are encoding, but it will be typically some correspond to some geometric operation that increases or decreases dimension by 1. And the names I mentioned will all kind of fit into this setting.
Okay, thank you.
You're welcome. Okay, more questions?
Maybe one more. In this last example of V, if we were to replace cart with the site of small, would there be any change in?
Even this one, replace this card?
Yes.
With what site?
The site of smooth loci, because
Yeah, that's definitely would be one option. Yeah, in fact, I mean, this site can be fairly arbitrary. There is not too many restrictions we impose. I guess maybe at some point we want to take stocks. So perhaps you want to say enough points, but I mean, that's certainly true for smooth loci. I mean, in fact, it's not really necessary. It's just a convenience for us. It's not crucial. Yeah, so this site can be fairly arbitrary. This site is basically much more rigid, and it must be a Cooling equivalent. It must give you something cooling equivalent to simplicial sets. Yeah. So this site is only serves to encode isotropies, and isotropies have a very specific encoding in our setting. Yeah. Okay, more questions? All right, so next time I guess we'll talk about the Bordism category one more, and perhaps we'll move on to defining the Bordism category, the ultimate Bordism category as it is actually defined in the paper. And since we already have all the necessary formalism, yeah, in fact, that's exactly what I already wrote down. Okay, and I guess that's it for today, and thanks for listening. And I hope next time we'll be now basically at the point where we can formulate the GCH properly. Well, at least the one part of it, the definition of the Bordism category.
Thank you for the
All
talk.
right.
For the
Yeah, you're welcome. Yeah, see you later, guys.
Bye bye.
Bye.